All right, let's talk about something that's both powerful and honestly a little terrifying. We're digging into the forces that can make an entire hillside, something we think of as totally permanent, suddenly just give way. Let's get into it. You see images like this all the time, right? These massive landslides that can just reshape a whole landscape in a matter of moments. But what is actually going on here? What convinces a huge, seemingly stable chunk of the Earth to suddenly start moving? Well, that's exactly the question we're going to answer. To really get a handle on this, we need to start with the name geologists have for it. It's called mass wasting. Yeah, it sounds super dramatic, but the definition is actually pretty straightforward. It's just a catch-all term for any time gravity pulls broken down rock and soil downhill. And the two key words there are gravity and weathered. This is just a totally natural process of rock breaking apart over time and, gravity doing what gravity does. And this right here shows that we're not talking about just one thing. Mass wasting can be this super slow, creeping slump that might crack a house's foundation over decades, or it can be a sudden, violent rock slide that just barrels down a mountain in a few seconds. So, if gravity is the main engine driving all this, let's take a closer look at exactly how it works on a slope. Okay, so on any hillside, you've basically got a constant tug of war going on. On one side, you have the driving force, which is gravity, always trying to pull everything downhill. And on the other side, you've got resisting forces, mainly friction, which is trying to hold all that material together and keep it right where it is. And this diagram, it lays out that whole battle perfectly. Look at the gentle slope down at the bottom. Friction is easily winning, and that boulder isn't going anywhere. Now look at the middle slope. Things are getting a little more tense. The forces are almost balanced. But on that really steep slope at the top, gravity's pull downhill is now way stronger than the friction holding it back. At that point, it's pretty much just a matter of time. So this brings us to a really fundamental idea that explains exactly when that balance finally breaks. The tipping point. So the big question is, how steep is too steep? Is there some kind of magic number, a specific angle where a slope is just guaranteed to fail? Believe it or not, there is. It's this awesome concept called the angle of repose. And you've actually seen this a million times if you've ever played in the sand. It's the absolute steepest angle a loose material can be piled up to before it just collapses under its own weight. If you pour sand out of a bucket, the little cone it makes, that's the angle of repose. But here's the catch. Not all materials are the same. Fine, round sand grains have a pretty low angle of repose, maybe 35 degrees. But coarser, more angular pebbles can hold a much steeper slope, up to 45 degrees, because all those jagged shapes create more friction and kind of interlock with each other. Okay, so now let's introduce the biggest wild card in this entire story, water. And water is tricky because it can be both the glue that holds a soap together and the very thing that triggers its collapse. Check this out. On the left, you see how just a little bit of moisture acts like glue. It creates surface tension that binds those sand particles together. It's why you can build a sandcastle. But then look at the right. When you add too much water, it fills up all the empty spaces, it physically pushes the grains apart, and it turns that stable pile of sand into a soupy, unstable mess. So water ends up playing three really critical roles here. First, rivers and waves can erode the bottom of a slope, making the whole thing steeper. Second, water is incredibly heavy. All that extra weight adds a ton of force to gravity's side of the tug-of-war. And third, as water flows through the soil, it creates something called seepage pressure. Just think of it as a constant push from the inside out, which actively forces soil particles apart and just weakens the whole structure. So, let's put all the pieces together. How do gravity, the slope's angle, and water all conspire to cause that final catastrophic moment of collapse? This brings us to a final really important concept, effective stress. The easiest way to think about it is as the grip that all the soil particles have on each other. But when water fills in the gaps, the pores between them, it creates pore pressure, which is basically a push outward. Imagine you're trying to hold a bunch of marbles together in your hands, but someone starts blowing air up through them. That air pressure pushes the marbles apart and makes it way harder to keep your grip. That's exactly what water does to a hillside. And this is the moment it all happens. Gravity is always pulling down. The slope's internal strength, its friction and cohesion, is always resisting. But when you get heavy rains, they add a bunch of weight and they increase that internal water pressure, which reduces the slope's grip. Eventually, you hit a tipping point where gravity's pull is just stronger than the forces holding the hillside together, and the whole thing fails. It's just a powerful, amazing combination of forces that are constantly shaping our world. And it leaves us with a pretty important question, doesn't it? As weather patterns get more extreme and rainfall gets more intense, how do we prepare for a world where the very ground beneath our feet is, well, increasingly on the move?